So, the lab we're doing, we're looking at the Ka of a monoprotic acid. So if we're going to look at a title for putting this together, what things might we want to include in our title? Ka and monoprotic acid are probably good ideas to include there. When it comes to your titles, I noticed a lot of people did this with the older lab, and for that matter with the text. Try to avoid using abbreviations. So instead of saying the Ka, you would need to say the acid dissociation constant. Okay. It's not that big of a deal, but it makes your report look more professional the less abbreviations you use. Okay. So those two things for sure should show up. Is there anything else that you're doing to determine it? You're doing a titration. Is there a particular special type of titration or titration? We're doing a pH titration. So we're determining the Ka of your acid, of a monoprotic acid, through a pH titration. The other thing that you will end up doing, even though the lab procedure doesn't clearly explain that that's what you're going to do until the very end, you're going to determine the molecular weight of your unknown acid as well. Okay? So I would expect all of those ideas to somehow show up in a pseudo-cohesive title. As the semester goes on, I'll be more picky with the titles, but as long as you're getting the main ideas in there, you'll get most of the points. And I might add in a few words here and there, but I'm not taking off points for that yet. Okay? As far as the rest of the report, you've got the title, you've got the methods section, which will be the first time that you guys have had to write the methods section. Most people do it wrong. Just the way it works. If you take a look at the good lab report on the course website, that method section, in my opinion, is awful. Do not copy the formatting of that. It's really, really bad. Okay? If you look at the Canvas website for your EDTA lab, that method section is much better. And then I've also posted an example method section of what I edited and all that fun stuff up on Canvas as well. So you can take a look at that to get an idea for how you should be putting it together. Okay? And what it's not for this lab, it's for, I think it's both of them are the EDTA lab. Okay, so it's a lab you've already done, so you know what the procedure said, you know what you did, and now you can see what somebody did just like you, but then turned it into words. Okay? Other than that, you'll do your results and calculations as always. We'll go through some of those calculations today. The rest of the calculations we'll do on Monday if you actually want help with that. Because your lab procedure explains how you're going to do some of those calculations in a little bit more detail to get better results. Okay? So I do expect certain levels of that, but we're not going to talk about it yet today because it's too difficult to analyze without some real results. And then you'll have the discussion and conclusion to finalize that. To do your discussion and conclusion, this is a good point that I forgot to mention to the Tuesday-Thursday section. You are determining the Ka and the molecular weight of your unknown acid. Okay? How could you verify in a discussion or conclusion whether or not you did a good job? Pretty much what it's going to come down to. You could go through and take a look at your Ka, and as long as it's not something that's wickedly huge, it's probably correct. So we're probably looking for something that's a weak acid, hence weak acid. It should be less than 1. Okay, so if your number is less than 1, in general, that seems reasonable. But molecular weight, we could throw all sorts of things at you. So the molecular weight may be massive, it may be really small. Okay, so you wouldn't know that unless you actually asked me for the results. So for the discussion conclusion, you're going to need to tell me what your unknown number is. And you'll actually have to tell me it. In fact, I can tell you what your acid is today. And then I will tell you the Ka of your acid and the molecular weight. You can then compare your result to that. Okay? Kind of makes sense? Okay. So if your result's really close, what would your discussion be? Results are close, and you did an awesome job. That's about it. Okay? If your results aren't close, okay, didn't quite do something right, so now go back through and look at the experiment and say why the experiment was wrong, not why you screwed up. Okay? So one of those things could be in the process of titrating. The indicator changed too rapidly, so you overshot the amount of base added. Okay? So things like that that could go wrong with the experiment. We're using a pH meter. Maybe the pH meter wasn't set up properly. It wasn't correctly calibrated to read the correct pH. Or maybe while you were taking it or using it, the pH fluctuated all over the place. It's again an instrument error, not your fault. Okay? So try and come up with reasons to explain why you got the wrong answer, but it wasn't your fault. Okay? That's what most discussions and conclusions are about. Go into science, that's what they end up doing. Oh, we got terrible results, but it wasn't our fault. It was somebody else's fault. Right? So push the blame. That's what I expect you to do with the discussion. Unless you did a good job, don't push the blame then. You can accept that. Okay?
That's a life skill.
It is. It's a pretty good one. As far as what material to introduce, you don't have to write an introduction, but we should discuss this. All of the concepts that would show up in the introduction should potentially show up elsewhere, like in your results and calculations or in your discussion and conclusion. So the things that we address here should show up at a later stage. So why we ended up doing this? We want to figure out the Ka molecular weight for an unknown acid, okay? Which could do a couple things. One, it could allow us to identify what that acid is if we know what it's supposed to be or have options of what it could be. Or we could just be adding to the general body of knowledge for that particular acid. Okay, so they are important physical characteristics of a compound, so they can be helpful to report and put out for the rest of the world to then use. Okay? As far as how we're going to go through and do this, we're going to titrate against a known base. Okay, why do we pick a base? Because it reacts with an acid. So what we're going to try and do is figure out the Ka and our molecular weight. To do that, we have to generate some idea of their concentrations of the individual species that make these things up. So we'll go back and use a reaction that we know these things react with. Just like we did with water hardness. To figure out the calcium concentration or our water hardness, what did we do? We reacted it with something that we knew it would react with, which happened to be calcium with the other one, the EDTA. Right? If we went and looked at the rate lab, right, we were actually looking at a legit reaction in that case. We weren't trying to identify something unknown. But how did we even identify what was going on within our reaction? We added a bunch of other stuff that then reacted with it. So in all cases, when we're going through and doing these labs, we're almost always adding something to force a chemical reaction to occur. That's something we want to know a lot about. Because if we know a lot about whatever we're adding to it, we can then infer what our unknown is, or get some information about our unknown. Okay? So what we're going to do is titrate against a known base. So you're going to make a base solution, and then you're going to add that to your acid very, very slowly and see what changes occur. Since we're looking at a Ka for an unknown acid, we could evaluate a balanced reaction. We're looking at Ha dissociating into the acid ion, or H+, and our conjugate base in an equilibrium expression. So we could look at our equilibrium being H+ times A- over the concentration of Ha. Okay? So if we want to figure out our K, we need to know those concentrations. Can we monitor those concentrations through any experimental technique? What does the pH measure? Concentration of H+. So what we're going to use is a pH meter to help us infer information about the concentration of H+, and hope that can get us information about the equilibrium constant. Okay, that's going to be our goal. We'll do that as we slowly titrate in, so we can get an idea of how much base is necessary to react with our acid, and then interpret some more stuff beyond that. So we will generate a titration curve in the process of this. So what are some complications? Okay, whoa, not next slide. Thank you very much. Appreciate that. we need to make sure that we know the concentration of the base. So the very first thing that we're going to be expected to do is to standardize the base. How do we standardize solutions? We titrate them against knowns. Okay? So we end up creating a new experiment so that we can determine our standard so that we can run the actual experiment we want to run. So that's where our standardization is going to come in. So you're going to first make up your base solution, and then you're going to titrate against a known species. Your base that you're trying to make would react with an acid. So the known that we should titrate against should be an acid. What is KHP? An acid. It could be better written, in my opinion, as HKP. Why do we call it KHP? What does KHP stand for? Potassium hydrogen phthalate. Okay, so we're just trying to pull the symbols off of it. Why do I want to pull the H out of there? Show that it's an acid a little bit better. Okay, so what we're going to do is titrate this against our base. What's going to happen?
Water.
We form water and I don't know what I was trying to draw there. Let's try that again. Still don't know what I'm trying to draw. KP negative, because it lost that hydrogen. Okay. We'll also add phenolphthalein. What's the point of phenolphthalein? It's an indicator that will indicate what? Indicates when our pH spikes. Okay. Why would our pH spike? Because we now only have OH minus. Why would we only have OH minus? Because we added enough base to completely react with our KHP. So when we see that color change, what do we know? We're at the equivalence point. Now everybody from lecture, what do we know at the equivalence point?
The initial concentration.
Our moles of OH minus added are, and we'll add that initial in here just to make sure, equal our initial moles of our HKP. This is the equivalence point. Yeah. Why is that helpful? Well, we're trying to figure out our molarity of OH minus. To get the molarity of OH minus, what do we need? We need moles and volume. Okay, so we just figured out moles if we know the initial moles of our HKP. How do we know the initial moles? This is a base. We measure something about the HKP. We measure its mass. What can we do with a mass? Convert it into moles. We now know the moles of our HKP. We can convert that into the moles of hydroxide. We can then get our molarity. Okay, so that's kind of nice. Why use KHP? Sorry, I'm trying to stick with this notation. Or HKP. Why not use some other acid?
Stable.
Stability is not going to matter too much with it. We could say it's not super reactive, so it's not going to be super dangerous to deal with. But there are plenty of other acids that aren't that dangerous. HKP ends up being one of the common standards for all titrations when we're trying to standardize a base solution. It's probably the most prevalent one. Almost everybody uses it. Why does everybody use that acid and not any other? What is that? Okay, it's a solid, which helps, but there are other solids that work. So we do want a solid that makes it easier to weigh out. Why not use acid? Or sorry, acid. Why not use HCl? Okay, I mean, that is a gas. The strength isn't going to matter. I mean, that makes it a little bit more dangerous, but that shouldn't be that big of an issue. Let's assume we can weigh out an acid, both acids, HCl and our HKP. Okay, when we weigh out HCl, let's say we measure out 0.1 grams. But we messed up a little bit and we didn't record one of our significant digits. It was supposed to be 0.11. So our mass is off by 0.01 grams. How does that translate into moles? Okay. If we convert that, I don't think it's worth writing up there. If we're off by 0.1 grams for HCl, and we convert that into moles, what happens? Should be 3645 grams per 1 mole. Uh-oh, I'm doing math. My math success today has not been good. Okay? And we get some mole value. What happens if we make that exact same mass mistake, because it's equally valid for both our HKP and our HCl? What's our molar mass for our HKP? When we go through to do our calculation, we want to know the moles. I don't care about the mass. It's all about the moles. If we did HCl, our mole error is relatively large, at least in comparison to our HKP. A small error in the mass results in a very small error comparatively in our moles. Okay? So when we go through to do a standard or standardization of any kind of solution, we typically want to use something that has a very high molecular weight, so that when we make a mistake measuring the mass, that doesn't translate into a massive error in our calculations. So that's the biggest reason everybody uses the potassium hydrogen phthalate. Okay? Why use phenolphthalein? It is an indicator. Why not use a different indicator? I'd stick with cheap. Better kind of works along those lines. It's probably just cheap. It's super, super common. There are other reasons to evaluate. We want an indicator that changes colors right at the pH for this transition. Okay? If we don't match up appropriately with our color changes, we'll be indicating something that isn't the end point of our reaction. Okay? So go through the textbook, kind of read through that. Kind of explains that. You don't need to go into any detail because you're not writing an introduction. Okay? The next part of this is what we're going to do with this data. So now that we've got our standardized base, you're going to go through, I'll talk about that in a second. We've got our standardized base. So now what we'll do is slowly titrate our base into our unknown acid and generate a pH titration curve. From that curve, we can use HH equation. What is the HH equation? The Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation will allow us to determine the pKa of our acid by just interpreting the curve without actually having to go through and do any fancy mathematics or ice tables or anything like that. Kind of nice. We can also figure out the molecular weight because at the end point of our reaction, we know that the moles of our HA initially equal the moles of base that we added. Okay, well, do we know how the mass of acid that we started with? What relationship can we get if we know the mass and moles of an individual species? We can get close, molar mass, or the molecular weight. Okay? So our end point gives us our molecular weight. Our half equivalence point, which we'll talk about, gives us our pKa, or our Ka value. Okay? Both of these calculations hinge around one piece of information. What is that one piece of information? To get this relationship, what do we need to know? We had to be where? What was that? Yeah, at the equivalence point. To get the pKa, I know I didn't show it up here yet, but those of you in lecture might remember. How did we get the pKa? When do we have the pKa? When we're at the half equivalence point. To get the half equivalence point, what do we need to know? The equivalence point. Okay? So our whole experiment centers around getting the equivalence point as accurately as possible. Okay? So we have to be super, super careful to try and nail that down as best as possible. Your lab procedure goes through and provides I think it's 3 different methods for determining the equivalence point from your pH graph. I expect you to do at least one of those methods. I think it might even be 2 methods that I'm going to ask for. Okay? They aren't too bad. It looks like a big mess, but Excel will do all the calculations for you. It'll be pretty straightforward. Okay? Questions about any of that so far? Yes?
You said that to get the equivalence point, we need the half equivalence point.
To get the half equivalence point, we need the equivalence. The equivalence point we can determine from our graph. I may have misspoke. Okay, so to standardize, I think these numbers are right. We need to make the NaOH solution. And the process of making it, we're going to make you make it from the pure sodium hydroxide. So you're going to weigh out solid sodium hydroxide to make your solution. Okay, a couple fun things with solid sodium hydroxide. Why would we use solid? It's easier to weigh out. Okay? Why is it a bit dangerous to deal with sodium or solid sodium hydroxide? It is a base, and it's a strong base. And it'll react with carbon dioxide in the air as well. Why do we not make you use concentrated HCl or concentrated sulfuric acid? Burns you, right? Both concentrated HCl and concentrated sulfuric acid, well, not sulfuric acid, but our HCl. Okay, is it pure HCl? No, pure HCl is a gas. So when you deal with concentrated hydrochloric acid, you're dealing with HCl and water. Okay? So we've kind of mitigated some of the dangers by incorporating water. Solid sodium hydroxide, strong base, same issues we have with strong acids. What's the concentration of our solid sodium hydroxide? It's effectively infinite. What does that mean as far as safety hazards go? It's going to burn you just as bad, if not worse, than concentrated sulfuric or hydrochloric acid. Okay? So please be extremely careful with the solid sodium hydroxide. Okay? When we weigh that out, that's where we come into all these other issues. It does react with carbon dioxide in the atmosphere. It does react with water that's in the atmosphere. It does react with water in your fingertips, among other things. So we don't want to touch it with our bare hands as well. Okay? Why does that become a problem with massing it out? Particularly as why we need to standardize it. What happens to the amount of sodium hydroxide, or the weight, as soon as we take it out of the bottle, put it onto the balance? It's going to start changing because we're now bringing water into it, or CO2 into it, which means the mass that we're actually obtaining is not just of sodium hydroxide, it's of a bunch of other things, which means we wouldn't be able to use the mass to determine the concentration of the solution. Okay? That's why we have to go through a standardization procedure. Okay? The other big issue, the sodium hydroxide, because it's extremely reactive, tends to react with the whey paper that you guys typically use. And if for some reason it got spilled on our electronic balances, because it's such a concentrated base, it destroys our balances, our electronic balances. So we don't want to weigh it out on the electronic balances. We have to come up with another way to do it. So what do we end up shifting to? Okay, we'll use the beam balances. So we'll go super old school and use, the weights and measures kind of balances. Okay. You could put it in a beaker. It comes down to how much does Mesa trust you to actually not ruin their balances. Yeah. So we need to measure some out. Okay, according to your pre-lab procedure, you already calculated how much you need to measure out, right? Everybody went through and did that pre-lab calculation? Okay, how many people didn't do that? Oh, wow, brave volunteers, nice. Okay, I kind of anticipated that people were not going to actually do that pre-lab calculation, so I actually already did it. For those of you that did do it, what was the amount that you're supposed to measure out? Roughly 2 grams.
Pretty close.
Okay. grams. So 2 grams is roughly what you need to weigh out. Because the pellet or the sodium hydroxide comes in a pelleted form as opposed to like a nice fine powder, it wouldn't be a powder because it reacts with water and it would solidify into a big chunk. That's why we do these giant pellets. We can be extra nice and rely on the Tuesday-Thursday lab, and when they measured out the 2 grams, they determined roughly how many pellets it takes to make the solution. So you can either measure out the 2 grams, or you can trust that I measured it appropriately, which, as of this morning, is questionable, that 12 to 14 pellets is approximately 2 grams. Okay? If you want to play around with the triple beam balances, go ahead, play around with them, and figure it out. You should get something, bless you, around 12 to 14 of the sodium hydroxide pellets. Okay? The next part is that we then want to make some standard KHP solutions. Okay? Pre-lab also told you to calculate how much KHP to measure out. How many of you did that pre-lab calculation? 8.7?
No, 0.7.
Oh, 0.7. Yeah, guess what that number is? Roughly 0.7 grams. Okay? Those calculations absolutely must show up in your notebook by the time you submit your notebook for grading. So you can cheat and use these numbers today, but I will be looking for those calculations. So make sure that they're nice and easy for me to find, because I know those are things we were supposed to do. Okay? At that point, we can then go through and do a series of titrations. We will dissolve the KHP in water first, because that makes it easier for the base to react with the KHP. You get it all in the same phase. Okay? You can use the stir plates, or you can do the addition and swirl at the same time method. I'm a fan of the addition and swirl method. If you would prefer to use a stir plate, you can. If you can't find them in the room, they're in the back room. You can talk to me and we can steal them out of there and shift them in. Okay? So to do your additions, you will need to get a burette from the stock room. You already have stir bars. You don't need to worry about that. Okay? So you just get the burette technically for this part. This says titrate 3 trials. You can do 3 trials unless you want to work in partners. You want to work in partners? Then do 2 trials. Okay? I would recommend that you make 1 base solution and then you split that base for each partner. So that way, by the time you finish with your 2 trials, you've saved time. If both partners sit and watch each other do the titration, you're going to end up wasting time. Okay? So it'll be a total of 4 trials per group of 2. If you're going to do it individually, you only need 3. Okay? At that point, we could then go through and calculate the molarity of the sodium hydroxide, average it for your trials, and then you would keep the NaOH solution in your drawer. That part of the procedure really only takes half an hour if you're efficient with how you've organized everything. Okay? If you're not efficient, that may take a little bit longer, in which case it probably makes sense to tag it with a label, put it in your drawer, and worry about the next part of the procedure next week. Okay? So, if you happen to be one of those fast people that gets through the titrations effectively, we can then go through to testing the pH. So what you'll need to do is get your unknown acid from the stockroom. Okay? Since you're doing this in partners, you only need 1 unknown per group of 2 people. Okay? You will both do the pH titration, however. Okay? So it doesn't really save you too much. You're both going to do it because the first person through, at least everything that I saw yesterday, will screw it up. Which means they can then tell the other partner how to not screw it up. Okay? So that you get the accurate amount of data. Okay? As far as the titration goes, it's fairly strict. Let's not get to the titration yet. We want to make the unknown solution. Okay? Your pre-lab tells you that you need to figure out how much of your unknown acid you need to weigh out. Okay? You all did that calculation because that was a calculation you're supposed to have done for Monday, right? Everybody already do it? Did anybody do it? Any guesses of how much you're supposed to weigh out?
14
Trick question. It's not 5 grams. I somehow did the calculation wrong. I'm not quite sure where 5 came from, actually. I've gone back and looked at all the math, and I have no idea what I did to get 5 grams. It's roughly 0.4 grams. Like I said, I have no idea where 5 grams came from. Not even in the right ballpark. Okay? So each student or each partner will measure out roughly 0.4 grams of the unknown and dissolve it in 100 milliliters of water. The procedure calls for a bunch of extra things. Don't worry about the extra things. That's how you prepare your solution. 0.4 grams, 100 mils of water. Anybody want to ask me about isopropyl alcohol? Don't use it. Don't worry about it. 100 milliliters of water, 0.4 grams of your acid. That's what you got to do. Okay? It may not all entirely dissolve. Give it some time to stir. Most of it will dissolve. In the course of adding base to your solution, the base reacts with the acid, making it charged, making it more water soluble. Okay, so it doesn't all have to dissolve by the time you start your titration, but by the time you finish your titration, it should all be dissolved. Okay? Questions about that? Okay. The pH meters are in the back room. So when you're ready to shift back there, what you will do is grab your burette, which will hopefully already have completely full of your base solution. You'll take that burette, your unknown solution made in a beaker with a stir bar in it, and you will move into the back room. In the back room, I can help you with the pH meters and make sure that you use those appropriately. I'll kind of teach you as you get in there. There's no point in me talking about it now. Okay? As far as what you need to record, this for some reason is very, very confusing. Okay? And it's probably because you get back there and panic because you see red. Red makes everybody panic. Okay? There's red solutions. It's okay. What you need to record is the volume and the pH. So you get in, you get your sample, your pH meter into the sample, you record the pH and your initial volume. You will then start to add base to your solution. As you add base, what's going to happen to the pH? It should start to go up. Okay? What we want is a whole lot of data points for this. So what we're going to do is add enough base to get the pH to go up by 0.2 units. That's 0.2, not 0.02. Just want to clarify. You'll get a lot more data if you add that extra 0 there, but it's going to take you forever. Okay? 0.2 pH units. Cannot clarify that enough. Okay? Somebody will mess that up. It's okay. Okay? As soon as you see the pH go up by that amount, record whatever the pH is and the volume. Then what do? Add more base. When it goes up by another 0.2, record the volume. What's your question? The volume of NaOH added. Yep. So at the end of today, you should have 4 trials worth of data if you're doing everything. At the end of the day minimum, you should have 4 trials worth of data to get you the molarity of your solution. Okay? If you push through to do the entire experiment, you will have at least one set of data for your pH titration, which will be a pH and a volume. Don't give me a change in volume, just give me the volume that the burette actually says. Okay? Hopefully, if everything goes super smoothly, at the end of the day, you'll have your 4 standardizations, and you'll have 2 sets of pH titrations, one from you, one from your lab partner. Okay? Then you guys can go home, plot your pH titrations, and decide which of your titrations looks better, and that is the one that you can do all your calculations for.
Okay, so just to clarify,
Yes.
you said when we record the pH and the volume, we're going to do that 3 times. pH and volume.
pH and the volume you're going to do twice. Each person does once. That will generate a lot of data. You'll have 30, 40, 50 data points.
Okay.
Your standardization, which you're going to do today, guaranteed. Everybody does the standardization. 4 trials. Each person does it twice.
Oh, sorry. You're going to, on this particular aspect.
When you get to this, each person does it once.
But you're going to measure, you're going to record the volume and the pH 3 times.
You're going to record the volume and the pH enough times to get the pH up to 11.5.
So we record every 0.2 until it gets up to 11.5.
Yep. What we're trying to generate, this will be a badly drawn one. We've got a pH and we've got a volume. You're starting with an unknown acid, so your pH should start pretty low. It's then going to increase as we add base and kind of level off until eventually what happens? It's going to spike. Then it's going to level off again. What we want is that you generate enough data that this is what your curve looks like. Okay? Which could be 50 points. It could be 100 points. Depends on how many pieces of data you're going to collect. Every 0.2 should get you roughly 20 data points. You should see a relative curve like this. Most people, if you do it for the first time, probably what you will see is actually something along these lines, where these are your data points, and then you'll get this. Okay? What happened in between? You missed it. Okay? You missed the spike. Ideally, you want data points in that spiking. Okay? It's not easy to hit those, because what's the volume change to get those? Like a drop. Okay? So your volume change is minimal, and you get a massive pH change. So your first attempt through, you don't know where that's going to happen necessarily, so you will probably miss it. Which is why as soon as you hit that spike, you quickly tell your lab partner. Now your lab partner knows that when they get to a pH of, let's say that's 5, that they should be going drop-wise because their pH is about to spike on them. Okay? So that's what this statement is then saying. When you start your experiment off, you'll probably, it doesn't ever get to 1 to 2 mils. You'll probably be adding about a half a milliliter to 1 milliliter to get your pH to go up by 0.2 units. As you continue along, it'll be roughly that same volume change until eventually it'll start to start to increase, start to fickle. It'll change more rapidly to the point where it'll spike. You'll end up dropping from being a half a mil to maybe 0.1 milliliters to then being a single drop. Okay, being almost completely irrelevant, now I'm going to make up words. Completely insignificant volume change. Okay? Yes?
Is that 5 pH kind of a rough estimate?
No. Everybody is different. Everybody's
So
different.
it's not like a specific time to look for.
Nope. That's why we're going to do it twice. The first person goes through, does it, so that they can warn your partner. That's the intent. Okay? Questions about what you're doing in the experiment? Okay, I don't want to get too much into the calculations yet, but we'll do this real quickly, at least for the Ka. If we were going to solve for the Ka, for this expression, what is it?
Backtracking just a second. When we do our
Yes.
pH titration, if we're doing the partners, do we need 2 burettes?
Yes. Every single person should get a burette. And then you only need 1 unknown per person. Or per group of 2. Okay? The stockroom will ask you how much of your acid that you are going to measure out. What's the number? 0.4. Okay? Tell him that number and he won't give you a hard time. Or he won't come yell at me for telling you the wrong number. Like he did yesterday. That was embarrassing. Okay, so we're measuring pH. So we should try and convert this equation into some format where we can see the pH. pH was, how do we solve for a pH? Negative log of the concentration of H+. So to get that incorporated, we can take the negative log of both sides. We get an equivalency here where we can pull out the H3O+. Okay, what is the negative log of the Ka? What is the negative log of H3O plus? Whoops. Okay. We want to know what our Ka is. We know the Ka is related to the pKa. So if we can monitor the concentration of H+, we would then need to know the concentrations of these. That gets a bit dicey. So what we can do is say, is there a point where that term disappears? Half equivalence. At the half equivalence, what do we know? A minus equals the concentration of HA, which means I get log of 1. The log of 1 is 0. So at the half equivalence point, I find out that the pKa equals the pH. Okay? We can pull the half equivalence point graphically off of our pH titration. Okay? So that can simplify things. If you wanted to, which you will have to do, tell me what the Ka is. What is the Ka going to be equal to? 10 to the negative pH. Okay? That gives us our Ka, and then we can all be happy with that. Okay, and the next part of this would be our titration curve. At the end point of the reaction, also known as the equivalence point, what do we know? The moles of base equals the initial moles of our acid. Okay, how do we figure out the moles of base? What do we know about the moles of base? What's that? We added a volume of it. And what else do we know about it? We could do the mass, but the mass isn't going to work because remember it reacts with the air. We did a standardization. The goal of the standardization was to get the molarity. So we know the molarity are moles per liter from our standardization. We can call that standardization of our OH. Now when we go through and do that, we've got the moles of OH minus, which equals the moles of HA. We want the molecular weight of HA. Molecular weight of HA is equal to the grams of acid per mole of acid. Do we know the moles of our acid? Do we know the moles of the acid? Yes, we can solve for that as we just did above here. Do we know the grams of our acid to make that mole amount? Yes, because we weighed it out. That was roughly our 0.4 grams. Okay? Questions about any of that? Okay. Like I said, as with most labs, the calculations will become easier once we've got some numbers to work with. In theory, at least one group will finish the entire lab today, which means on Monday we can put that into an Excel file and start to play around with some numbers so you get an idea of what you need to do. Okay? We'll make that the first group to give me results, or actually how about the first group to get everything today. We will run through calculations with your numbers on Monday. So there's your reward for being the first group. Okay?